Who are we missing? Mr. Liu's here. Math ladies. Alex. Can you stand up and show us your shirt, Ken? So when we designed this thing, all the logos were supposed to go on the sleeve, and that was the last version they showed me. Now turn around. Instead, they put this skunk stripe down the back. Thank you. And they have studiously avoided me since doing this, but that's okay. Did you get one of these, Cam?
Yeah, but that's why I was wearing a suit.
Yes, we discussed that, I know.
I didn't know that was the time.
It was supposed to all go on the sleeve. They were supposed to be like 2 inches max. But you can see where my authority is. My power. My mojo.
I wasn't given a rough draft at the time.
And if you had, what would you have done?
I would have run it by you, of course.
Would you have done the skunk stripe?
I don't know, because we kind of look like a soccer team. But
Or NASCAR?
yeah, that's true too.
Yeah. I noticed they haven't discussed it with me post-meeting, but that's okay. See, sometimes when you're the old guy who tells and yells, you just have to be quiet when things, you know. And by the way, thanks everyone for not getting arrested and not doing anything stupid and generally being well behaved. Okay. Mr. Desai, show us your t-shirt, please. Can you sing the song? That coyote is really a crazy clown. You don't know the song? Come on, man. You can't wear the shirt if you don't know the song. What do we got tonight, Joker?
That's Deadpool on the Iron Throne.
Like Transformers or something? Or
So what? Well, that's Deadpool. And that's the Iron Throne from Game of Thrones. It's all new stuff.
yeah, well, we all know how we feel about new stuff. So this is really old, and it's going to be really painful. But when you're done, and by the way, I did see the gentleman who had the mental breakthrough on this lecture some 20 plus years ago. I saw him at the ATCE, but he's forgotten all this. But it was remarkable to watch after this lecture when he, I get it. So hopefully that'll happen tonight. Okay, tonight we start with the continuity equation for each phase. You can see we have the continuity equation for the oil phase, the water phase, and the total gas. And remember, when you're dealing with gas, what are your options? You have the so-called free gas. You have the gas which is liberated from oil. And then you have the gas which is liberated from water. Now, in theory, we can also have, I guess I should be over here, a term where oil is liberated from gas, but we usually don't treat it that way, do we? We don't treat the continuing equation for oil that way. Why? That's not the way a black oil works. Okay. What works that way? A condensate, correct. So if we're sitting here tonight in 2017 talking about this, and this was actually derived in the late 50s, early 60s, they were mostly thinking about black oils. What happens when you go to a condensate system? What are you probably going to have to do? Anyone? Sorry? Okay, we'll have to add the term if we treat it that way, but most condensate systems are going to be represented by a compositional formulation. Black oils have really nice correlatable properties, so we can always say that the gas is going to come out of the oil, the gas is going to come out of the water. And there was a paper written in the 80s, or a series of them, I guess, where they did allow oil to be liberated out of the gas, but that's a relatively small fraction. And by that, I mean in the reservoir. Okay. How many of you have heard of the white oil scandal? Anybody? The white oil scandal? No. So in the early 80s in Northeast Texas, there was, and also in the Panhandle, I need to be clear on that, sorry. There was a situation where people had gas wells, and this operator had the rights to gas, and that operator had the rights to liquid. So in order to achieve maximum liquid rates, what would the operator do? Chemical engineers? Chemical engineers?
Increase pressure.
What would they do? Sorry? Hammer it down? No, think about, or you guys are thinking linearly, think nonlinear. What about reducing the temperature at the wellhead? So they put refrigerators on the wellheads, and what happened? They dropped out a bunch of white oil. What is it really? And what kind of condensate is it going to be? Extremely volatile. What's going to happen when that condensate, the temperature goes up? Poof, it's going to reflash. This was billions of dollars in lawsuits. Billions. And you look back and you laugh. But, you know, sometimes the oil industry has quirks, and this is one of them, where somebody has the gas, somebody has the oil, and the guy getting the oil, he's going to do whatever he can to maximize the production of that. Now, you're right, they could have run it through more separators, but their goal was just to knock it out. And so they, you know, probably several thousand wells maybe. But at any rate, I digress. So now we go and we start talking about conversion of densities to formation volume factors. We're not going to work in density. Historical tidbit. Ready? Historical tidbit. Anybody in here with a pure science degree? Math ladies? Pure science? You like pure science? You don't want to be bothered with engineers, do you? No, very good. What about anybody with a physics degree? No? Yeah? You got a physics degree? Not physician's degree, physics. Physics engineering. So kind of like a little bit of physics and a lot of engineering, or a lot of physics and a little engineering combined. Okay, so 50-50. Alex, physics? What do you remember? Nothing? Okay. So who is the greatest petroleum engineer that ever lived? And no, it was not me. I'm sure one of you is going to try to tweak my ego. Don't do that. And no, it was not any professor at University of Texas either. Apparently they like to present themselves that way. And I'm sure they're listening tonight, so I'll get a nasty email tomorrow. The greatest petroleum engineer that ever lived, my personal opinion, was Morris Muscat. He wrote books in the 30s on reservoir engineering that we still use today in some fashion. He's a brilliant guy. And what was he? A physicist. Okay. All of his solutions are formulated in terms of density. I think he missed that day in petroleum engineering class. We don't work in density, we work in pressure. So what we're going to do here is we're going to convert density to formation volume factor, and of course we will work in pressure. But just as a little tidbit, he did work in density. We're also going to write Darcy's law for each phase. Now, we haven't talked about this, have we? Now, I had a technical committee meeting this week, and I tried to get a couple of my people motivated to propose new things. And it wasn't intentional. Everyone knows Bill O'Reilly, the Fox News host who got fired for, well, being a Fox News host. And he wrote all these books. And what were they? Killing Lincoln, Killing Jesus, probably Killing Blasingame will be the next one. But so I was at a meeting a couple of months ago where a famous professor from another university gets up and he says, I'm not here to kill Darcy. I'm not here, to to diminish it. And Mr. Bake, this is kind of your area. He was thinking about nanoscale transport. But, you know, everybody laughed and it became a tagline. So, you know, we're not here to kill Darcy. We're not here to kill ARPS. We're not here to kill Muscat. We're not here to kill Ramey. We're not here to kill Archie. We're not here to kill Standing. All of these guys were pioneers in petroleum reservoir engineering. But it's absolutely without a doubt in the next 10 to 15 years, you're going to see solutions which are formulated not on traditional reservoir engineering theories, but on something else. There will be computational tools and so forth. There still will be room for this. Our understanding of bulk performance won't change, but our desire will be to represent at a smaller scale. So for right now, we're going to use Darcy's law. So there's a permeability, an effective permeability for each phase. There's a viscosity term for each phase. And then there's a gradient according to the phase. Now, we haven't talked about gradients according to the phase, but they were pretty much, how would you differentiate, sorry, bad word, how would you distinguish a gradient from one phase to another? Well, it's obvious because we know the difference in pressure from one phase to another is called capillary pressure. So we'll have to make some conjecture about the relationships of the pressures between each phase. What's the easiest thing to do, Cam? Which is neglect capillary pressure. And then what happens? The pressure in all the phases is the same. Okay, that was quick. We'll come back to Cam in a minute when we need to cheat again. So is everybody okay with this? We have a continuity equation and we have an equation of motion for each phase. So we have a continuity equation for each phase and an equation of motion for each phase. And yes, if we were talking about a compositional formulation, this would look a lot different for the mass balances. We would have to account for each species. We're not going to worry about that tonight. And frankly speaking, that is a tremendous amount of work. There's the amount of work that goes into compositional simulation for just the phase behavior part is probably equal to or greater than the work on the simulation of the spatial performance. Okay, so now we convert and we represent our equations in this fashion. We're going to have an oil flux, which is the density multiplied by the velocity. And of course, we're going to use formation volume factor. So we have this oil density term hanging around, but our familiar KO mu O. Then we'll have water density multiplied by water velocity. Again, just multiplying through. And again, we'll use the formation volume factor. So we have a water density at standard conditions. Again, KW, mu W, BW, and then delta PW, of course. But for gas, it'll be a little bit different. Even though we can write it as a total, we're going to have Kg, mu G, Bg, and then multiplied, of course, by the gradient of gas pressure. Then RSO, KO, mu O, BO, multiplied by the gradient of oil pressure. And then RSW, KW, mu W, BW, multiplied by the gradient of water pressure. A really quick question, I didn't ask this. What's a typical number, and I know everybody hates the U.S. engineering system, but just give me a typical number of an oil gas oil ratio for black oil. What do the textbooks tell us? Somewhere between 400 and 2,000, something like that. Okay. Maybe a little bit lower, 400, 1,600, something like that. So that would be classified as a black oil. How much gas comes out, and that, sorry ladies, that's cubic feet per barrel, which is a really stupid number, but sorry, I know you want meter cube or meter cube, but that's how we report it. So it's cubic feet per barrel. So that's how many cubic feet of gas will be liberated per barrel of oil. What is it for water? What's a good number? Sorry? Where we? 0.1? 0.1 what? Okay. All right. Just want to make sure I knew what the units were. Anybody else want to take a guess? Somebody have a... What about that Pellegrino you've got in front of you, Mr. Bake? Yeah. Has it got gas in it? How many cubic feet of gas do you think come out of that can whenever you open it? It's more. It's going to be more than 0.1, right? Why? Because they inject CO2 at what, about 10 bars, I think, something like that. Maybe 15. It's going to be a little more than 0.1. Does anybody want to take a guess? Gabe? Holy.
Wait, are we talking about the like
We're talking about formation water. Okay, so we have our boundary now. 0.1 to 1,000, so a factor of 10,000. Anybody want to take another guess?
500?
Okay. Did you guys never watched Let's Make a Deal, right? Did you? You watched Let's Make a Deal?
Sometimes.
That guy died a couple of weeks ago, and the radio announcer said, I wonder if he goes straight to heaven or takes the deal behind door number 3. That's terrible. Okay, so who wants, the price is right. I can tell you, you two are way high, okay? And you are way low. So, anybody else? Maybe you were thinking Bitcoin, okay? Anybody else? 10. 10 is about mid-range, minimum about 5, and a maximum about 30. So let's just quickly have a discussion about that. You know that most water in the Gulf Coast region is charged with natural gas, right? And let's pick an average. Let's say it's 10, just so it's easy. Okay? How many cubic feet do I want to produce to be economic? Gabe? 1 million cubic feet a day would mean how much water? 100,000 barrels of water a day. Is that a lot of water, class? That's a hell of a lot of water. And that's just for 1 million cubic feet of gas. Okay? Let's say that we can produce that water for free. Now you have formation water probably on the order of 60,000 parts per million salt or dissolved solids, whatever you want to call it. How much is it going to cost to dispose of it? Mr. Desai? This is America. You can throw your trash away for free, right? If it were free, how much money would you make? Is this a business model to produce natural gas out of charged water? What do you think? Now, this is 2017, but I can tell you that between 1975 and 1985, actually even into the 90s, the federal government of the United States spent a small fortune studying this. Several companies drilled wells within government cooperative projects. They were successful whenever they found higher than 10, maybe 20, 25 standard cubic feet per stock tank barrel or standard cubic feet per barrel, and whenever they could dispose of the water for free. Now, they even concocted an idea of where they would construct a pipeline and run it offshore, okay, about 30 miles. And that pipeline would simply release all this water at the bottom of the ocean, and it wouldn't affect anything, right? Not too sure about that part, but that was a concept. When you start to put things back where they don't belong, things happen. But at any rate, we'll leave that alone. So there's no business model for this. You guys agree? So if I came to you with a business plan and said, I want to drill a bunch of wells in charged aquifers and produce the natural gas, what's your first question going to be? Well, your first question is going to be, are you crazy? But what's the second question going to be? How much gas are we going to produce? What's the third question going to be? How much is it going to cost to get rid of the water? Okay. This actually could be a viable model, but what do you think? Alex, would you invest your money in it? Would you invest Uncle Sam's money in it? What if I gave you a tax break where you got $10 a million cubic feet for that gas? Sorry, not just a tax break, but an incentive price. Is this the socialist states of America? Well, to hear your friend talk on Fox News last night, it was. But we're not going to do that, are we? There was a time when there was an incentive price for tight gas. It was $10 an MCF, roughly equivalent. Who cannot make money at $10 an MCF? Anybody? And what goes up must come down. So sooner or later, the subsidy is going to run out. At any rate, I just wanted to ask that. So what's going to happen to that RSW term, you think? Cam, since you're the king of the cheaters, can we neglect it?
Yeah.
Well, we're going to carry it all the way through, but eventually we could probably neglect it. Very good. Okay, next, we're going to set up the mass equation. So these are the flux equations up here, and then we're going to set up the mass equations. And before anybody gives me some nasty gram about doing politics in class, this really happened. We spent a lot of money on trying to produce natural gas out of charged aquifers. So, and it's research. So why not? I just think they forgot that you cannot dispose of the water for free. And end of the story. Okay. So now the oil mass equation is going to be the porosity times density for oil. And of course, we're going to go ahead and write that out as porosity density saturation because it's how much oil is there. And then we use the relationship for formation volume factor. So we have porosity density saturation divided by formation volume factor. Exactly the same thing for water. Now on the gas side, what do we have to have, class? We're going to have the free gas term, which is here, the gas from oil term, which is here, and then the gas from water term, which is there. And when we factor all these out, that is porosity times gas density, we have this, and we have this. So now we've got all of our equations set up, and what we're going to do is achieve a final form. And the gas equation is going to look like this. The oil equations are going to look like this. And the water equation is going to look like that. Now, at this point, what have we neglected, Cam? Just the capillary forces. Okay? We're saying that all of these pressures are the same. Is that okay? Probably not going to kill anybody. Okay? That's the only assumption we've really made so far, other than this is a black oil system. Now, if we neglect the saturation gradient multiplied by the pressure gradient for oil, the saturation gradient multiplied by the pressure gradient for water, the pressure gradient squared terms, what's going to happen is it's going to reduce to this, and to this. Now, are equations 8 and 9 familiar to you? Yes, we derived those last week. Okay. Equation 7's a little bit ugly, but it should be familiar to you as well. We also assumed a few different things about the behavior of those properties, but we'll come back and talk about it. Okay. When you derive this is required in the notes or in your assignment. You need to make sure you're paying attention to these derivatives. Okay? And as I mentioned, the derivation of this entire relationship is in the notes, so you'll be able to find that. Okay. Next is what happens. There's the magic step, like when your professor was making a derivation and they do a magic step. So this is relatively easy, getting to this point. Now you still have 3 equations and you want to combine them into one. 3 equations and you want to combine them into one. Math ladies, how do we do that? How do we combine 3 equations into one? Don't even think it. Okay, how do we do that? I've got 3 partial differential equations. How do I combine them into one? Now you can see the bottom 2, I set them equal to the gradient squared term, and I probably work out a relationship there. Anything else? Sorry? We'll probably have to do a bunch of algebra because we're going to have those two equations which give us a combined relationship, and then another equation which goes into 7. There's a lot of steps here, but algebraically, this is going to be relatively straightforward. So what's going to happen is we're going to take those 3 equations and crush them into one. Okay. Again, this is the Perrine-Martin concept. Who was Perrine? Perrine was the first guy that did this, and he showed that the total mobility is related to the mobility of the water plus mobility of the oil plus mobility of the gas. Total compressibility is the same thing. Compressibility of oil multiplied by saturation of oil. Compressibility of water multiplied by saturation of water. Compressibility of gas multiplied by saturation of gas. And then add on the formation compressibility. He proposed that in a paper, I think it's like 1955 or something. Martin comes along, and remember, Martin worked for Creole Oil Company in Venezuela. You can even still see the old Creole Petroleum Engineering building in Maracaibo. It's kind of run down and not being used, or at least it wasn't when I was there in 2000. But they had some really smart people there, and Mr. Martin was one of them. He was on seconded, I guess, from Exxon, maybe, I don't remember. And he had some time on his hands, so he wrote a 3-page paper on how to write these equations. So his equations 7, 8, and 9 are here, right? Then what happens? A magic step occurs. And that magic step, Mr. Martin came up with equation 10. Mr. Martin came up with equation 11. Mr. Martin came up with what else? Equation 12. He did not label it, but the total mobility relationship is here, and the total compressibility relationship is here. And again, he didn't label them, but they're not numbered, pardon me, but they're there. So the combination of 3 equations into one led to the total mobility relationship, and it led to the total compressibility relationship. Has this been done before? Yes. And who did it? It all goes back to Muscat. Muscat did the total compressibility equation, and he wrote it in terms of, well, he actually wrote in terms of equations 10 and 11. He wrote saturation, pressure derivatives. He may have formulated this slightly different, like using the material balance equation, but it all kind of converges. Okay. Now, how does that make you feel? Well, you haven't done this exercise yet, but I can assure you once you do this exercise, you're going to feel a lot stronger, a lot tougher. Somebody's going to need to open the door for her. Okay? Does that make sense? That going from 7, 8, and 9 to 10, 11, 12, and the 2 intermediate equations, it's going to change your life. I mean, I'd like for you to drop everything and work on this tomorrow and come back to class and say, I'm a lot tougher, I'm a lot stronger. You know, nobody here was in the military, right? But you'll feel pretty tough, except for comedian. Have you ever thought about being in the military? Yeah. I watched a training film on the Marine Corps. You'd fit in really well there. You know, if you can't follow orders, do you know what they make you do? They make you break rock or concrete with a sledgehammer for about 3 months. You get a break every 15 minutes. You can't talk. You can't talk back. Because if you talk back, you get another month or something like that. You know, I think what they called it was professional development. Yeah, that's okay. All right, so we'll leave that for now, and I'm going to skip over. These are the notes where I derive 7, 8, and 9, and then we'll talk a little bit about Blackwell properties. Just very quickly, you know, above the bubble point, there is a slight change in the formation volume factor as a function of pressure. Below the bubble point, I know this is not a straight line. In fact, I know not what it is, but you know, you've got an inflection point here, and then the same thing for the solution gas oil ratio. Above the bubble point, the solution gas oil ratio is obviously constant. Below the bubble point, it's quasi-linear, I guess you could say. Damn it. And then the same thing, viscosity above the bubble point looks like that. Why does viscosity above the bubble point look like that, class? Chemical engineers? You want a demonstration? No? Yeah? Okay, Gabe, Mr. Bake, Cam, Eric, up here. This is going to be your finest moment. Unfortunately, you're probably going to knock my headphones off. Okay, everybody come in here. And I want you to recognize that you do not have the opportunity to beat the crap out of me here, but bounce around like molecules. No, this away. Keep, you know. Okay, so you got more room, so bounce around. All right, but as I increase the pressure, what's going to happen? You got less room. I feel like, you know, this is not going to go the way I want it to, but all right. So the higher the pressure, the more molecular interactions, the more what? The more viscous. Okay, great. Thank you. Yeah, the pressure's off now. You can go be diffuse molecules. Okay, so what happens below the bubble point? Why does it explode? More specific. Sorry? The lighter components come off, you have a heavier fluid. So the above the bubble point is molecular interactions. Below the bubble point is the changes in the fluid properties, right? So how do you identify the bubble point? With which one of those? Okay, you're right that they try, whenever they actually measure viscosity, that is the check on what is the bubble point. You could also do it with a cell and watch for the first bubble of fluid to come out. That would be the bubble point as well. But a check, a validation, if you will, is to check the viscosity as well. Is it expensive to run a viscosity experiment? Okay. Okay. So it could be expensive to measure that. What about gases? And I know I'll talk about gas in a minute, but what do you think about gas? Gas viscosity should be relatively easy. Okay. In theory, it's actually okay. Sorry, I shouldn't say theory, but concept. But in practice, the methodology, because it's not a fluid, you know, it's not a liquid, it's a gas, it can be more difficult. Since 1965, we've been using the Lee, Gonzalez, and Aiken equation, which was developed by what is now the Gas Technology Institute, but then it was the Institute of Gas Technology. See how they flipped it around, but that's okay. And it was sponsored by API. I put the report out there somewhere, but they only ran 8 gas mixtures, and they only had 8,000 psi maximum pressure. So they had 8 mixtures and 8,000 psi, and that equation has been used for over 50 years. You know, the companies that reported fluid behavior weren't even measuring gas viscosity. They just calculated. But again, when you're requesting a fluid report, you probably want to do that. You probably want to ask for gas viscosity, or you probably want to ask for oil viscosity to be measured. Okay, above the bubble point, this is the compressibility of the oil, which makes sense because if you look at the formation volume factor, it's kind of linear. And then what happens below the bubble point? Mr. Desai? Why is the oil compressibility jumping so much? because look at this. It is two-phase, but it's also highly dependent on the shape of the RS curve, right? Okay, class. How many of you have had Dr. McCain's phase behavior class? Anybody? Yeah, did you like it? Okay, what did you learn? Okay. Okay. What are you guys laughing about? He took it, you didn't. And Dr. McCain says Mother Nature only takes her feet off the ground one time in petroleum engineering, which I don't know if that's true or not. But where is that, class? It's at the bubble point. What happens to the compressibility, Alex? It jumps by a factor of 5 to 10. Is a factor of 5 to 10 a lot? Yeah. Why don't we see this feature in reservoir simulation? Because it doesn't happen everywhere at the same time. Okay. But this compressibility feature is a major headache because above and below the bubble point, things are substantially different. Good. You guys kind of got the hang of that. All right, we're not going to worry about this. What I was trying to show is that 1 over mu OBO, its shape. Now, I know you're going to laugh, but is this relatively constant? Relatively speaking. Even when we go logarithmic, maybe not quite, but here and here. So what's your thought on this? Can you get away with assuming mu OBO is constant? Sort of, maybe. If it is constant, then we don't need pseudopressure. If it isn't constant, then we do for an oil. Now we'll talk a little bit about the behavior of mu OCO, which is the oil viscosity multiplied by oil compressibility. Is it constant? And then we look at it in a log-log sense. What's the slope of this line, class? It's almost 2. Is that a lot? I'd argue that's pretty not constant. Okay, so the behavior of mu OCO is not going to be very helpful, is it? Okay, and of course all this is below the bubble point. So another little factoid. And then dry gas, we already know about this. This is mu Z versus P, and we've talked about this before, both for steady state flow and for the development of the diffusivity equation. And then the same thing for P over mu Z. We recognize this is never constant. And then for mu G CG, we also talked about that. Now the interesting thing here is that this function is almost a slope of 1, so there's almost a 1-to-1 relationship. But the interesting thing here is it's much greater than 1, almost 2. So very, very different behavior. So back when I was young and foolish, I was asked to teach a lot of industry short courses, and I happened to cross paths with some folks that had an interesting definition of the formation volume factor. Of course, it's the volume at reservoir conditions is divided by the volume at standard conditions. I hope everybody's okay with it being a mass or a density definition. Is anybody not okay with that? I know it's a volumetric behavior, but ultimately it's defined on mass or density. So we should be working, math ladies, in density or mass, but we're lazy. Why do we work in volume again? Because we sell barrels of oil. We don't sell tons, we sell barrels. So this is why we work it this way. Now the typical values for oil are 1.2. Where does a black oil end? Probably about 1.5, maybe 1.45, something like that. And then I've gone on ahead and written 2.4, but Alex, do you remember what Dr. McCain told you for critical fluids or for condensates? You know, things are going to get really, or volatile oil is going to get really high really fast. Now, viscosity, gas viscosity can be, gas formation volume factor. My brain's on viscosity, sorry, can be pretty low. I usually report gas formation volume factor in barrels per MSCF, because I want to convert everything to equivalent liquid by using that definition. But there's a definition, or there's some sample values. Now let's go to viscosity. And this is what I was saying about, working with these other guys. They called it a sort of internal friction. Does that sound right, chemical engineers? That viscosity is a sort of internal friction? In layman's terms, the molecules are rubbing against each other. So the viscosity itself is the proportionality of shear rate to shear stress. It depends on pressure, temperature, and composition. Oil values, and this is not heavy oil, obviously, but medium, would be about 0.2, which would be a really light oil, to about 30 centipoise, which would be a medium oil. Gas is going to be about 0.01 to 0.05, so roughly a factor of 5. And then water can actually be below 1, 0.5 or so if it's gas charged probably, and then about to 1. So there's some typical values just to keep in your mind. And then fluid compressibility, we already saw this. These are the definitions that we would have to derive for the case of the Perrine-Martin type behavior. We have the first term, which is minus 1 over BO dBdP. Often not really reported quite like this. Sometimes a minus sign is taken out and dBdP is assumed to be positive. But of course, dBdP for the oil case is negative. That is above the bubble point. And then, sorry, I'm jumping around. We need DRSO dP. What's the derivative of a constant class? 0. So above the bubble point, this term's 0. Gas, we're just going ahead and assume that we're dealing with only gas itself. That's going to be minus 1 over Bg dBg dP. And then the same thing goes for water. If there is a component of gas coming out of the water, then you can use this formulation as well. Typical values of oil compressibility for pressures above the bubble point are about 5 to 20 times 10 to the minus 6 reciprocal psi. Again, apologies for the units, but this is standard stuff. And then about 30 to 200 for a volatile oil. Gases can be very high. They can vary from 50 to 1,000 times 10 to the minus 6. And water, you can just guess 3 to 5 times 10 to the minus 6. So that's not a bad guess if you're in that ballpark. Formation compressibility is the ballooning nature of the formation. It's inflating with pressure. So formation compressibility is the porosity change with pressure divided by porosity or normalized to porosity. So a normal, so-called normal pressure gradient or a normal formation compressibility in a normally pressured reservoir might be 2 to 10. I don't know if any of you remember the Hall correlation, but the Hall correlation was actually pretty low. It was about 3. So if you have to guesstimate a number for formation compressibility, probably the number 3 would be okay. Abnormal pressures can be very high, the compressibility for abnormally pressured systems can be very high, sometimes 10 to 100 times 10 to the minus 6. Okay. Again, all these are just typical values. Math ladies, I know that this sort of thing is probably boring, but it's important to understand that these parameters have physical meaning, and that's why we're going over it. Okay. So now we'll go quickly over the diffusivity equations. We've already done this for the gas equations and for the oil equations, but we'll do it for all of them now. So the first one is a black oil. We derived this one the other night. It does have this nonlinear term, and what we're going to do is assume that for small and constant compressibilities and small pressure gradients, that term goes away. Cam, is that a bad assumption? Probably not. It's probably okay. Okay. And then for black oils, again, we can look at the behavior of the formation volume factor and the behavior, say of the viscosity if you want. Again, looking at what happens at the bubble point, and we're going to have to think about how that affects this behavior. or this assumption of the nonlinear term. And then, of course, we have this tremendous jump at that point. Now let's talk about solution gas drive. This is where the pressure is below the bubble point. So if we go back, we're talking about over here, we're talking about over here, and we're talking about over here. So what do those functions look like? Well, technically, we're supposed to use an oil pseudopressure. But if this term is constant, then this becomes just pressure. So that's okay. So let's ask ourselves, is this really going to be constant? And we talked about this a minute ago. Not really, but probably okay. So for those of you who are paying attention, it's not really constant, but you could probably ignore it. Okay. Now, unfortunately, the behavior of the MuOCO product or term is not well behaved. It is a huge change over a short distance in pressure. I mean, just look at this behavior. It's a factor of, or an exponent of almost 2, maybe 1.5. And since this is never constant, some bad things are going to happen. And again, I'm not trying to play gloom and doom here. I just want you to recognize that when you're looking at a very volatile system or even a black oil system, you probably should be using numerical solutions for it, or in terms of some of the vendors, they do offer a pseudopressure solution. They do not offer a pseudotime solution, but that's okay because there's usually an internal numerical model tied to it. If my words are going too fast for you, what I'm saying is, yes, this is a serious problem, but there is a way around it, and that would be to model the problem numerically. And then my good friend Dr. Camacho, in his dissertation in 1988, was nice enough to make my life a living hell. And he and Dr. Raghavan plotted the behavior of the, what did I just do? I scooted the whole thing over. How do I grab this? Like that. Okay. See, that wasn't so bad. Now, the real question is, where does this occur? And of course, these are small dimensionless times, and what you're seeing is that small dimensionless times, what is this reflecting? This is the average compressibility divided by the average mobility. So this is reflecting the single phase above the bubble point behavior. That's this. And that's true for all the cases that are modeled. There are 4 cases that are modeled here, 2 different sets. Okay. And then after you go through the bubble point, you again have this essentially constant behavior. And the nice thing about this is it also confirms Perrine-Martin theory, which is that the compressibility and the mobility can be treated as a constant, and you can represent multi-phase flow with total mobility and the total compressibility terms. If I haven't made this very clear, let me say it again. Down here is the above the bubble point behavior. Down here, over here is the below the bubble point behavior. And fortunately, since these are constant, this verifies the Perrine-Martin theory that those behaviors are constant, and hence the multi-phase equation could be used. Now, somebody needs to be a smart aleck and say, okay, Tom, you're so smart. What happens in here? And I don't have a simple answer there. I just don't have a simple answer here. I can tell you what I think, but my best guess is that you're probably not going to be harmed too much by this. Most of the time, you're going to be looking at below the bubble point behaviors, so you can probably tie your analyses to these values. But, when I was about your age and initiating a big project, I had to consider what this change meant. And we do not have this information as a function of pressure. We do not have it. It doesn't exist. So you're going to have to make a decision. Do I go with the below the bubble point behavior, which is over here, or do I go with above the bubble point behavior? What's going to happen if I use the compressibilities above the bubble point? Am I going to underestimate or overestimate the volume? This is a binary. You can't miss. It's true, false. It's going to be one or the other. Who wants to be the guesser? Mr. Liu? Lower compressibility means what? To balance the material balance, what's going to happen? You're going to have a larger volume, aren't you? Okay. So if you're making a calculation with the above the bubble point behavior, you're going to get a much larger volume. Okay. Be careful with that. Be careful with that. Be careful with that. And I know you're saying, well, you don't know the right answer, so how do you tie it together? You have to make a decision that you're on the right-hand side. Now, if you're really smart, you would say, well, you can't do that. Why? How many of you went to a contentious paper at the SBE meeting? Anybody? Nobody did? You did? Which one did you go to? Okay, so we won't talk about that because that one had me in it. But I will comment that a student from another university who saw my tag said, does this happen often? Because it was obviously their first meeting. And I said, well, in my 40 years, it's happened once. It just happened just now. But when I presented the first work on RTA, which was a paper on estimating reservoir volume using production data analysis, I presented it in Mexico. And I want to confess that, I thought of Dr. Camacho sort of as a competitor. And he got up in a very disciplined way and said that RTA could not possibly work. And he cited this as why. And I turned white and, crawled back into a hole and hoped for the best. But this is exactly why RTA can work. Because he showed that you don't have to track the whole system. You have to track the part of it where you're operating at. And again, it's a logarithmic scale, so it may be a little confusing. But where's the vast majority of your time going to be? On the right. So everything's okay. Yes?
If you're producing the middle zone,
The middle zone is going to be like that, though.
but if you are, then how are you going to, is there a way to, how are you going to know?
The only way to do this is to simulate it. And all of Raghavan's students, whether it's Camacho, Jones, Vo, whatever, whenever they were validating pseudotime for liquid and volatile systems and condensate systems, they all used a simulator. So if you have a simulator, you have the answer. So what they were doing was formulating the pseudotime behavior but they have the answer. I have to look at the practical problem. We don't have the answer. So what I want to know is how much error am I going to generate by using the right-hand side relationship to estimate volume. And, you can argue it could be significant, but at least it's consistent. And you heard me correctly. I'm basically saying you're wrong, but it's consistent. And if you're consistent, then you can map it. You're not using this to estimate reserves. You're estimating in-place volumes. Reserves are estimated from production, correct, everybody? In-place volume is estimated from matching against some sort of model. So what we're doing here is we're creating an estimate of in-place volume. Now, somebody in this room is smart enough to know what? What would be the easiest way to fix this? Don't calculate a volume. Leave CT out of it. Calculate in CT, not in. So take the compressibility term out of the situation, and you could map the product of, or you could solve for the product of volume multiplied by compressibility, and then map that. And we did some of that as well. Okay, I warned you before about where pseudopressure came from. 1942. 1942. The indefinite integral may be evaluated as done for the two-phase system and the pressure distribution may be determined. However, it will be sufficient for the calculation of the productivity factor to consider only the limiting form. That's a lot of words for what? Just assume it's constant. This function. Okay. We're almost there. We did this the other night for gas. We took the basic relationship. This was equation 5, if I remember correctly. And we then solved equation 5 by making certain assumptions, certain developments. Well, we didn't make any assumptions on this part, but we made some developments. We ended up with the pseudopressure time formulation, pseudopressure pseudotime formulation. You can see those down here. Now, what we're going to do next, of course, is, and we've already seen this, but this is where we said that the gas compressibility, gas viscosity term was approximately 1, a slope of 1. Now let's look at the dry gas case in terms of the pressure squared formulation. And again, we started with this equation, and we worked through all the algebra to derive this. So this expression says that the log of viscosity times z factor, the derivative of that with respect to pressure squared, what do we need that to do, class? We need it to be 0. What's the quickest way to make it 0? If this is constant, what happens? The whole thing falls away, and that's exactly what happened. Okay, so if that's true, and down here that's constant, then we're okay. Or, looking at a log-log sense, if we're over here, that's okay. Okay. Next is the last set of equations, which is the mu g over z over, or mu g z over p, and again, that's the natural log of that. If it's constant, then the whole thing falls apart. But remember, it's not constant. It's not constant. This looks constant, but this is not constant. Right? Same over here. This log-log form is definitely not constant, and this really isn't constant either, so this is never valid. Now, the last slide is a summary of the Perrine-Martin equations, which is the whole purpose for this lecture. And again, we showed how to take and derive all of these, the so-called gas, oil, and water equation. And then we're going to take those, and after a hell of a lot of algebra, you're going to derive the Perrine-Martin relationship. What are some of the assumptions, again, that you have to make in order to do that? You have to assume that there is no capillary pressure, or that all the pressures in the phases are the same. What else do we have to assume? That the pressure gradient multiplied by the pressure gradient, so that pressure gradient term squared is equal to 0, and also the pressure gradients multiplied by the saturation terms, saturation gradients are 0. Is that true everywhere? No. Where is it not true? At the wellbore. Okay, that's where the most action is going to be happening. All right, and then finally we have the total compressibility and total mobility relationships, which are derived as a part of this. I strongly, strongly advise, if you haven't started deriving this, to please get started deriving this. This may be the worst in the whole scheme of things that I have you do. This may be the worst. Okay. All right, and the 5 minutes that are remaining, I just did a Trump. Jeez. Okay, in the 5 minutes that are remaining, here's what I'm going to propose, and I want you to sleep on this. I want you to tell me tomorrow night. Don't send me an email. Let's talk about it tomorrow night. I'm thinking about taking the list of reading papers and coming up with some sort of a lottery or a selection or something where you rederive everything in the case that you select, and that's your final exam. Okay. Wow. That didn't get anybody's attention. Now, Alex pointed out that in the past I've given the provision of allowing you to select your own problem. And that has been a disaster. Why? Why? What's 99% of the problem? That would be 0, yes, but what about number 1? You don't know how to set it up. In order to solve it, you have to set it up. So it's probably best in a class like this to look at something somebody else has done. Now, if you want to propose a problem that you can set up and solve, I'm all ears. But there probably will have to be a proposal submitted to me by you to do that. Okay? I'm not trying to rush anybody, but I would like to get this settled before the 1st of November so that if we're going to do this, then we do this. So tomorrow night, we'll have a democratic discussion about this at the end of class, and you guys think about it. And if you want another paper not in the reading list, that's fine with me. But everyone will have a different problem. Okay? Let me repeat that. Everyone will have a different problem. So if 3 of you grab the same thing, somebody has to make a decision. What I'll probably do is let you guys beat the hell out of each other and see who gets it. No, I can't do that. But, huh? Yeah. I bet old Joker here could take you. Yeah. It wouldn't be that. It'd be when he comes out with that garden claw, and whacks you upside the head with it. You don't.
Too much energy for me.
Is that right?
I start to die out.
Yeah. Well, who knows? Maybe you could nail his foot to the floor or something.
Still here.
Oh, sorry. I thought you were gone. So what do you think? What's your first impression?
He wants to drive it the same way everything.
If you could derive it another way, that'd be pretty damn. I'd say that'd be pretty cool in my book. So what I will expect from you is probably like a small report, like a small SPE paper. Let's say 5 pages text, another X number of pages, figures if needed, and then a short presentation, something like that. Or, but you have to do it very well.
Can we each, you said lottery system, so we do this.
No, it'd only be if somebody chose the same thing.
So to clarify, we just do the work in the paper on our own, in a way.
Yeah. And if you have a problem, you can talk to me or Alex. But like Eric said, if you come up with another solution for it, I'm going to be damn impressed. And there will be some actually that some of the older work, there'll be other solutions for, or maybe you could propose an alternative. I mean, how do you feel about this? Does this? Cam, tomorrow, try to bring that, roll of duct tape that we talk about, periodically. Yeah. And Mr. Bryan, will you please bring a tennis ball? All right. I mean, how do you feel? Do you want something like that? I'm trying to think about if I were in your shoes, what would I want? Look, you guys have been really good. You've come to class. I hope you're working behind the scenes. If you wait until the last minute, the volume of work you have to do is going to kill you. I'm going to tell you, if you're not starting pretty soon, some really bad things are going to happen in your life. And, they, well, I mean, you've got 2 months, right? It's 2 months from yesterday that it's due. And you guys are all like, 2 months? Hell, I don't know what I'm doing tomorrow. Yeah. Oh, is that right? Okay, well, whatever. So, thank you. A month and a half or thereabouts. How do y'all feel about it? Yes, no, maybe? Okay. I'm not saying it has to be unanimous. I mean, I could assign the final like I was thinking of before, but I think something like this would be nice. Math ladies, any comment? No? Have you seen anything that you've read that you really like? Sorry? Very difficult? Okay.
It's like how oil smells.
Did you ever watch All in the Family with Archie Bunker? His wife would just blather on and he would ignore her. So he goes like that.
Is that what you do when I talk?
Mostly, yeah. I think of things like that, you know. All right, well, why don't you think about it? And again, you know, I've made a lot of mistakes in assuming what students wanted to do. I guarantee you, I can write a final exam that you will love to hate. I can also tell you that this proposal that I'm giving you will be harder than the final exam I give you. But it'll be you against you. And if you do well, you know, I mean, even if you don't solve it, but you do your best, I'm going to be impressed. But if you, you know, put it off till the night before, we'll see you next year, you know, I guess. So, I was also thinking about maybe giving a list of other kinds of problems you could solve. How do you feel about that? But that's a lot more work on my part. And I can tell you, I know what's going to happen. You're going to go, it didn't work. It's your fault. Okay. Well, let me see what I can do. Nothing? I got nothing. What's a rough hand show? No?
You can give us the list of the other problems.
That'll be probably. I was going to ask if you guys would mind meeting over the weekend so we could catch up, but that's probably not going to go over very well. Maybe. Does anybody argue? I mean, you don't have to be here. Okay, well then we'll meet on the weekend too and get caught up and get. I think we can get completely done by next Friday. So, but remember, I got to be out on Tuesday, Wednesday, Thursday. I got to go somewhere on. So Tuesday night I'm flying and Thursday night I'm flying back. But Friday, I think we can finish all up. Ooh, that'd be great. I like that. Let me think about it. You know, maybe I can just. If you guys kind of give me the weekend, let me think about a list of possible problems. But unfortunately, it'll be biased by my prejudices. Let's do a straw poll tomorrow night and see how you feel. I'm not married to this. Everybody understand that? It's just an idea. I thought you might like it, but I guess it's like asking you if you want to pay more taxes and go to the dentist. So, all right.